All right, guys, so we're going to start topic 10, beam deflection, which is, this is going to be the last topic that I post. And if you got these slides from Titanium, make sure you download them after this video is posted because I changed the slides a little bit. I added some information, took out some unnecessary information. So just so that we're all using the same slides, make sure you download them now. Okay, so another quick note, actually, you'll see that these are, or this topic is about 80 slides long, so don't be worried about that. We're not going to go through all 80 slides. We're going to go through the important slides. Let me get rid of this text box. Sorry. We're going to go through the important slides here, okay? We don't really have enough time to cover all of these methods of deflection, so I'm going to kind of just go over the ones that you're going to see on your final, and we'll kind of just go from there. Okay, so what are we going to discuss for beam deflection? We have all of these different methods that we can use to calculate deflection of beams. And this is a super important topic because it kind of leads directly into structural analysis. So you'll see that when you get into structures, to some extent, you'll kind of pick up where this class left off. And what we can do with these methods of deflection, in addition to finding deflections and rotations, is actually use these methods to solve for indeterminate structures. So you'll see here that's kind of like point 2, and we're not going to actually get to cover this in this class. So I'm going to write here, and I put this in the slides later on, but this is an extra topic. Okay, and you'll see me skipping a lot of slides in this, and that's just because I don't want to cover extra information that we don't have time for. So I'm kind of going to cover what's going to be on your final, which is kind of a hint, or I'm just kind of straight up telling you guys. Okay, so here we're going to start with first understanding what the elastic curve is and understanding what deflection and rotation is. Because I know those words are sometimes words we commonly may use, but what do they actually mean and what do they represent in terms of a structural system? So before we get into calculating these actual values, what do they mean? The first thing we need to know is what the elastic curve means. Whenever you see the elastic curve, this is going to be somewhat of a representation of the deflected shape of your structure. Okay, and when you get to structures, you'll be asked a lot to draw this shape. So it's good to start recognizing what those support reactions mean again and how you can draw what's happening in terms of loading. Okay, so let's take a look at this beam over here and let's define some things. So we see that the beam has this horizontal axis, okay, and this blue curve, this is the deflected shape due to that force P. So the beam has deflected some shape due to a force P, and this, if we're looking at, let's say, just this point on the beam, this here, this distance, it's a distance, this is our deflection at that point. So you can see that deflection, just like shear and moment, varies depending on where you're standing on the beam. So deflection, we use a couple of things to determine, or to a notation in terms of deflection. We can call this Y, as you can see, because it's in this vertical direction for beams. You'll also see it as delta, and you'll also see it written as this fancy little V shape. So whenever you see this fancy little V shape, I'm going to always draw these two little tails on the V so that we never confuse this with shear, because sometimes that gets a little bit confusing. But any of those, they just mean deflection, all the same, just different notation. Now, in terms of rotation, let's look at the rotation at point A. So how do we figure out the rotation? Well, we draw a tangent line, okay, and then we draw the tangent line to the original shape, and we see that there's some angle that it's changed by, and this angle theta is the rotation. Okay? You can see here, point A has rotation, but point B does not have rotation. This tangent line is the same, so theta is 0. But that makes sense, right? Because this is a fixed support. And we know at fixed supports, we cannot rotate. So it's forcing that beam to stay steady there. Okay, so you want to kind of think about those things when you're drawing this elastic curve or drawing the deflected shape like this. Okay, and again, one of the most important applications, of course, in addition to determining deflections, because those are also very important, especially when we're designing, which is not often, but when we're dealing with brittle material. We do design with concrete a lot that's brittle, but we kind of reinforce it with steel and do a couple of other things to mitigate that brittleness. But we don't necessarily design an entire building with glass and no other support. So it's not as common, but we do definitely need to limit our deflection for structural integrity purposes, but also because deflection helps us figure out how to analyze an indeterminate system. And we'll talk a little bit more about this. You'll definitely talk more about this in structural analysis. Okay, so let's continue talking about the elastic curve here. Basically, the elastic curve is not difficult to draw in general. And what we can do is, if you do have a structure that is more challenging to draw and you don't really know how the loads are going to affect the system, what we can do is we can use the moment diagram to construct the elastic curve. And I'll show you how we can do that with this example. Okay, so we have a beam here, and it has two loads placed on it, P1 and P2, and we have a roller and a pin. So let's say we're going to draw the moment diagram for this system. Okay, we'll have, of course, starting with 0 moment, ending with 0 moment, no moment applied here. Let's draw some vertical lines. Okay. And what happens here is we have some value of moment that shifts to this point. We have some value of moment that would shift to this point. And we would have to have this come back and close at 0. And this is our moment diagram. And a couple of things that we can note here. We can note that this whole area is negative, and that this whole area is positive, right? So what we know about the elastic curve here, which is the shape, this deflected shape, we know, let me continue drawing these lines here. And then we have some important points C and E that are already drawn for us. So what we know about this, if black is our original line, right, we have a roller support here. The black line is our original beam. We have a roller support here. We have a pin support here. Draw it in blue. We know that at P1, we're going to definitely deflect downwards some, I'm going to call this delta, right, the deflection. We're going to experience some delta A here. It's going to definitely push down at A, and it's going to move down. Okay, we know that we're going to have 0 deflection at the roller, and 0 at the pin, because that's the definition of a pin and a roller. We can't move. Okay, and what the other thing that we know is whenever our moment diagram is negative, that means our elastic curve is concave down, which is like a frown, and whenever it's positive, that means that our elastic curve is concave up, like a happy face or a cup. Okay, U up and then down like a frown. Okay, so all we have to do, if this is concave down, that means from here to here, I definitely have to have concave down. And the reason I've drawn C here is because at some point here, we know that it changes and it goes to concave up. So we call this point C some kind of inflection point. Okay, we have some kind of point where it changes from this concave up to concave down. And that's generally this elastic curve. Okay, we can do the same thing with this beam here. So we can start by drawing the moment diagram. We're going to have some negative moment here. It's going to be pushed up. And then no change here, and this rotation back to get it down. And here we have negative, here we have a positive. So when we come to draw our elastic curve, again, this was a fixed support, so this is where it's really important to first start with the support. If this is a fixed support, we know for sure that for some portion, we're going to have 0 rotation and 0 deflection. We have no support here, so we know for sure we're going to get some change, some delta C. If we start off, I'm going to draw a little line here. Okay, we know we have to be some kind of concave up like this, down first, sorry, down like this, and then we're gonna go some kind of up here and something like this, okay? And so we just have to remember that we have no delta or theta at fixed supports. Okay, there's no support at C, there's nothing stopping it from moving, so we definitely have some delta there. Okay, so we've already talked about this concept of moment curvature when we were deriving the bending stress formula. So I'm not going to go into this anymore right now, but I will let you review these slides again. But they are the same, it's exactly the same thing that we derived all for bending stress. So if part of this doesn't look familiar, go back to the bending stress topic and review it. But for the sake of time, I'm going to kind of skip through this and get to the point. So what we can do is we can actually determine slope and displacement through integration when we get down to this formula here. Okay, and just to be very clear, this is actually, let me scroll up here so I can show you what's happening. This value of deflection, they're using this V here, okay? This V, this little V. I'm going to either use delta or Y to make this a little bit easier so that you don't ever confuse it with shear. But the book does use this little V, so all of these equations that are copied from the book are going to have a little V. And if you're reading the book, it's going to have a little V. So just be careful with that. Okay, so here I'm going to go until we get what we're looking for. So this is the big picture here. This is what we're going to use to solve for our slope and deflection. So if you go through this derivation, what you'll see is from our moment curvature relationship, we can actually determine our slopes and deflections through the load, the shear, and the moment. So we can use the shear, the moment, and the load to actually take the derivatives and find our deflections and rotations, which is really cool. Okay. So in terms of sign conventions and coordinates, basically, we're going to use the same sign conventions that we had previously used when we're deriving these formulas. And this is super important when we're doing this because we all want to make sure that our signs are appropriately reflected on our diagrams so that we're getting answers that match up. Okay, let's talk a little bit about boundary conditions. So this is very important regardless of what method you're using and in a lot of applications. So these need to be, you can memorize them, you can remember them, or you can do whatever you need to do so that this is kind of ingrained in your mind. The first one we're going to talk about is the roller support. And generally a roller support, this is a review from statics a little bit, but generally a roller support is drawn like this. And what we know about a roller is that there's no deflection that can occur in the Y, 0, but we also have no moment resistance. I'm going to shorten this as NMR because I'm going to write that quite a bit. And then we also know that theta cannot equal 0. There has to be some rotation because it can rotate. Okay? Now, number 2, we have the pin support. Typically, a pin is drawn as a triangle. We know that we have delta Y is 0. We can't have a delta X either. We have no moment, I keep putting in our no moment resistance. And we know that theta can't equal 0. Okay, next we have fixed supports. We typically draw that as a straight line like this. We know we can't move in the X, we know we can't move in the Y, and we know that we can't rotate. Okay, pretty easy. Room here. Okay, the next one we have, number 4, is a free end. So a free end basically means it has no supports. We have no shear resistance, and we have no moment resistance either. Okay, and the last one we'll discuss is the internal hinge or internal pin or a hinge. It's called both of those things. And that looks something like this, a little circle in a beam. And all we know about this is we have no moment resistance. Okay, so remember these when you're solving problems. This will help you a lot in determining the elastic shape, the elastic curve, the deflected shape, and it'll help you in your future classes too, for sure, for structural analysis as well. Okay, so let's get into an example now. We have a simply supported beam, and it's subjected to this concentrated force that's shown, and we want to know what the maximum deflection of this beam is. Okay, so the first thing we're going to do is let's draw the elastic curve here. And I'm going to show you how we can do that without having to draw the moment diagram when it's a simple loading like this. So at point A, we know that we can rotate, but we can't have any deflection. That means that it has to stay there, but I can have some rotation. Same thing for C, I can rotate. So I'm just going to connect those, something like this. Okay, and this here is my elastic curve. Okay, pretty simple. Now, we can see that our moment function changes at point B. So we're going to have to make two cuts here to figure out what M is. Okay, because we're going to actually, let me scroll back up here. We're going to be plugging into these formulas here. Okay, so because of that, we can see we need MV and the load, which we already have the load. Okay, so we're going to make two cuts here. So let's do this here. And when I make that cut, I expose, I'm going to draw these with this positive sign convention, some M1 and V1, and I'm going to call this X1. And I have no load on this. So you can see here that M1 is equal to 2X1. Okay, and now our cut number 2. Our moment changes after the 6 kilonewton load is applied. So here's my cut 2. I still have a 2 kilonewton. I have 2 meters until I apply the 6 kilonewton load. I'm going to have some V2, some M2, and I'm actually going to call this entire part X2. And if I solve for M2 here, I get 2X2 minus 6 times X2 minus 2, and I end up getting this equation. M2 is 4 times 3 minus X2. Okay, now I can get into my slope and elastic curve. So I'm going to use my moment 1, which is defined from x1 till 2. And you can go back and see those equations. I'm going to use d squared delta 1. I'm going to change them from v to delta because I don't want to confuse it with shear. I know that's equal to 2x1, just so we know v is equal to delta, this little v. And I'm taking the integral. So once I take the integral of both of those, I end up getting this. And I can take the integral again to get EI delta 1 equals 1 over 3 x1 cubed plus c1 x1 plus c2. And I have now an equation in terms of delta 1. And I can do the same thing for my moment 2, which is defined between 2, x2, and 3. And I have EI d squared delta 2 over d x2 squared is equal to my moment function. I can take the integral and I get not d squared, d delta 2 equals 4 times 3x2 minus x2 over 2 squared. And then I have plus another constant of integration. And then I can take another integral, and I can get EI delta 2 equals 4 times 3 over 2x2 squared minus x2 cubed over 6 plus c3x2 plus another integration constant. And now what do I have? I have equations, but I have all these constants of integration that I need to now deal with and solve before I can do anything. Okay, so how can I solve for C1, C2, C3, and C4? I need to evaluate these using boundary conditions. What do we know about boundary conditions? So we go back to our problem and we say, well, I know a couple of things about this beam. I know that at x equals 0, my deflection has to be 0. And I know that at x equals 3, my deflection also has to be 0. And this deflection, x equals 0, falls within x1, and this falls within x2. Okay? I also know a couple of other things. We call these, so these are our boundary conditions. Okay. I also know some information about my continuity of the beam. I know that, so I'll say one continuity condition. I know that the derivative, this d delta 1 over dx1, has to be equal to d delta 2 over dx2 when x1 equals x2 equals 2. At that point too, I know that this has to be continuous, right? Whatever happening before has to happen after. And I also know that my delta 1 has to equal delta 2 at this x1 equals x2 equals 2, because it has to be a continuous piecewise function. I can't have a break there or it's not a function. Okay, so now I'm going to use this information to come back. I'm going to use all of this information to solve for constants of integration. Okay, so let me come back here and plot. Let me see how much room I have left so I can ration. Okay, so I'm going to come back here and I'm going to say, well, delta 1 equals 0 at x1 equals 0, and I'm going to plug that into the first equation, and I get all zeros for C2, so I get C2 equals 0. I also know that delta 2, this was delta 1, equals 0 at x2 equals 3. And if I plug that into the equation, I get 4 times 3 over 2, plugging in 3. And I can't really solve for anything here. I have a C3 and a C4, but now I can say that d delta 1 over dx1 at x equals 2 is equal to d delta 2 dx2 at x equals 2. And if that's the case, I can plug both of those in and equal them to each other. And now I have C1 and C3. Can't solve anything there, but I can also plug in this. So it's just a system of equations now. And I have to see what I can use to solve for all 4 constants. Plus C3 times 2 plus 4. And if I solve all of these equations, I get C1 equals negative 8 over 3, C2 equals 0, C3 equals negative 44 over 3, C4 equals 8. And now I want to plug these back in to my equations so I can get my complete equations here. Excuse me. Okay. If I do that, I get EI d delta 1 over dx1 is equal to x1 squared minus 8 over 3. And EI delta 1 equals 1 over 3 x1 squared minus 8 over 3 x1. And now for number 2, EI d delta 2 over dx2 equals minus 2x2 squared minus 44 over 3. Okay, and if I wanted to find the max deflection, which is what the problem asks for, I need to remember that max deflection occurs when slope or derivative equals 0. So basically max delta occurs when d delta dx equals 0. So I just need to set that equal to 0 and figure out what that number is. So here, I'm going to take my delta equation, x1 squared minus 8 over 3 equals 0, and I get x1 equals 1.633. Now I have my other delta equation, which is right here. Let me see. I'm going to do it with both of them so I can figure out what the right answer is, right? So 12x2 minus 2x2 squared minus 44 over 3 equals 0. If I do quadratic equation here, I get x equals a negative 3.667 and I get a 9.667. Neither of these numbers work. Take out the negative. The other one doesn't work on our beam because it's less than that many meters. So I'm going to pick the one that works here. If you have multiple that work, you can plug them in and just solve for your max deflection. Okay, now I'm going to plug this back in. I get EI delta 1 equals 1 over 3 times 1.633 cubed minus 8 over 3 times 1.633. And I get negative 2.90 over EI kilonewtons meters cubed, and the negative means that it's going downwards. Okay, and that is my answer for example 1. Okay, so example 2, you're using the same method and applying it to solving for the deflection, the displacement deflection. I'm not going to go through this and solve it because it's like the first one, but you guys can try this one on your own and make sure that you get it. We're kind of going to move forward to the conjugate beam method now. Okay, so this is definitely going to be on your final. I'm going to put a star here. And I'm going to put a note. So it's pretty hard to miss if you watched this video. Okay, I can't make it more clear than this. So you're going to have a problem on your final where you have to solve for deflection and you have to use the conjugate beam method to do so. Okay, so I'm going to go through this part a little slower, and then I'm going to write some stuff down, and then I have some parts that are already written down that's kind of for you to go over and review on your own. So the idea behind the conjugate beam method is you get to solve for slope and deflection by only having knowledge of statics. Okay, so this really tests your knowledge of statics though, because with that being said, if you are not good at drawing shear and moment diagrams, this is a good time for you to brush up on that, okay? Because it's going to hurt you in the conjugate beam method if you're not really good at that. But at the same time, if you are good at that and you did well in those concepts in statics, then this should be really easy for you to pick up. So the conjugate beam method is based on two main theorems. The first theorem, number 1, basically says, and this is written, I believe this is paraphrased later, or it's not paraphrased, it's here, I can just read them. So the slope at a point on the real beam is numerically equal to the shear at the corresponding point in the conjugate beam, and the displacement of a point in a real beam is numerically equal to the moment at the corresponding point in the conjugate beam. And I can see how these don't quite make sense yet, but they will make a lot more sense once we go through an example using the conjugate beam method, okay? And the value of this method, the reason I'm going to talk here about the value of this method is because when you get to structural analysis, or even here you can see we have a lot of different methods that we can use to solve for displacement. And we have to start weighing our options of which one's the most efficient. Which one's the easiest to implement for a certain type of problem? Which one is the most universal? So you have to kind of list pros and cons for each method, and the value here is that you can solve, so I'll write this down, you can solve for displacements and rotations using only statics concepts, which is pretty cool. Right. Okay, so before we get into an example, let's talk about kind of, this method seems a little bit tricky before you kind of implement it, but then once you get the hang of it, it's actually very easy to understand. So I'm going to try to go through this slowly. So let's take a step back and remember our shear and moment diagrams. Okay, we remember that the derivative of moment, dm dx, is equal to shear, right? We also remember that dv dx is equal to the loading, right? And if we kind of take this in and put it here, we can say that d squared m over dx squared is equal to now the loading, okay? There's a very similar relationship that we can draw with shear and moment versus moment curvature. Okay, and I'm going to put this information here in these columns. So I'm going to say that we know dv dx is the load, and we know that d squared m over dx squared is equal to the load. And we know here that d theta over dx is equal to m over ei. This is moment curvature. And we know that d squared y, or delta, over dx squared is equal to the moment curvature, m over ei. And now you should start to see this kind of similarity between these two items, okay? They're similar. That's what we want to notice at this point. Here we have a first derivative, load m over ei. So, and here we have d theta over dx, here we have d squared y, or d, this is y, which is also equal to delta, which is this little v thing. Okay, this is displacement. Okay, so what happens if we take, this is where things get kind of crazy. We take this m over ei. What happens if we take m over ei and we replace our load with m over ei? That means that if we're solving for dv dx, we're really solving for d theta dx. And if we're solving for d squared m over dx squared, we're really solving for d squared y over dx squared. And that's all you have to understand about this method in order to do it. Okay, so let's continue. Here is the book's kind of rundown. Okay, actually, let me write this one last part out in case you didn't make this connection, just to try one more time. So we're saying that v is equal to the integral of the load dx. This is similar to theta, the rotation, m over ei dx. Okay, and we have m equals the double integral of the load dx. And then we have y, which is displacement, which is the double integral of m over ei dx. So if we treat this like the loading, if we treat this, make this the load, all we have to do is statics to get the slope and displacement. And that's basically what this kind of shows you. The conjugate beam basically means this is our real beam, but instead I'm going to turn this into a conjugate beam by loading it with m over EI. Okay, and here, these are the theorems. Okay, now the next kind of interesting point that we need to remember here. I suggest for now you try to understand this, but you also kind of memorize / remember it the best you can. You can also use this on your exam, so it shouldn't be a problem. But make sure you get how to switch these. So what we have to do is when we're drawing the conjugate beam, okay, when we're drawing the conjugate beam, we have to be conscious of what we do with the supports because they're going to change. Okay, the shear and moment that develop at the supports are going to correspond to the slope and displacement of the real beam and its supports. So we need to make sure that we're not messing up the shear moment versus slope displacement for the conjugate beam. So if the real beam has a roller support, that means we have 0 displacement and non-zero slope, which means the conjugate beam must also be supported by a pin or roller because we have 0 moment. But the tricky part comes if we have a fixed or free end. We have both slope and displacement are 0, and the conjugate beam therefore has to have a free end because there they'd have 0 shear and moment. Okay. So here, what we want to do is we want to, if our real beam has a pin, our conjugate beam has a pin in the same place. Real beam has a roller, conjugate beam has a roller. Okay, this is where things get interesting here, remember, and free. These are the main ones we need to really remember here. If our real beam has a fixed support, we will remove that for the conjugate beam. If our real beam has a free support, we will add a fixed support in the real beam. So make sure you remember that. And these are some examples of real and conjugate beams. This is a good one here. You can see that we had a fixed and we had free, and now we have free, fixed. We just switched them for a cantilever. Okay. All right. So we're going to go ahead and go through this example here so that we can understand basically exactly how to implement the conjugate beam method and what that kind of looks like. Okay. Alrighty. So we need to determine the slope and deflection at point B of the steel beam, and the reactions have been computed already for you here. 5 kips going up, 75 kip foot for the moment, and we have an E and an I value. So the first thing you always want to do is you want to draw the shear and moment diagram of your beam. So this is kind of step 1. Shear diagram. And of course, this is super important, our moment diagram. Okay. And here, we're going up 5 kips. No change. Down 5 kips. And then nothing. Here for moment, you can see we have this negative 75. Let me draw a line here. We'll pretend that line intersects in the right way. Okay. And then we're going to go up here. That's pretty much it. And now what we're going to do is we can construct our conjugate beam. So here, all we have to do, this is the most important thing. If this A was a fixed support, it's now free. B was free, now it's fixed. You're just going to do that from the table. Okay. And now the load on our new beam, this is our conjugate beam. Let me write that here. The load on our conjugate beam is just going to be whatever you see on the moment diagram. and I'm drawing it going down negative, just like I would on some real loading. This is a triangular distributed load. Negative 75, right, going down, but it's going to be 75 over EI because that's that moment curvature relationship. Okay. And now all I have to do is analyze this when I get, so here, this is the conjugate beam. So V of the conjugate beam is equal to the rotation of the real beam. And then M of the conjugate beam is equal to the displacement of the real beam. This is that delta value. Okay, so now this is going to be a quick analysis here. Let's do this. So we have our resultant here. This is still 15 feet right here, 15 feet. 15 feet. We need to calculate our shear for the conjugate beam, our moment for the conjugate beam. Okay, and we can sum forces in the y direction, set them equal to 0. We get negative 562.5 over EI, that's this here, minus VBC equals 0, and we end up getting VBC equals negative 562.5 over EI equals negative 562.5. Now let's plug in 29 times 10 to the 3 times 144 for the conversion times 800 inches to the 4th times 1 foot 4th over 12 inches to the 4th inches to the 4th, and that equals negative 0.00349 radians, and this is theta at point B on the real beam because it's the shear on the conjugate beam. Now we can do the same thing. We can sum moments, and we get 562.5 over EI times 25 plus M conjugate beam B equals 0. We get the moment at point B on the conjugate beam is 140.62.5 over, this is in KSI, again same conversion, and we get 800 divided by this 12 to the 4th, and we end up getting negative 0.087 feet, and this goes to now delta B, convert to inches, and we get negative 1.5 inches. It's negative because the slope of the beam was measured clockwise and the displacement is downward. That's why we have these negative values. So this is clockwise, this is downward, which makes sense. Okay, so I'll post one more video with the next example, but for now, let's make sure that you guys understand this part and that you're good to go before we move on.